Topping of marine gas turbines using 4-port wave. Abstract propulsion power plants of sea-going ships have to produce power at low fuel consumption, but they are subsequent to emission legislative constraints. Marine two-shaft aeroderivative gas turbines are used either as exclusive power plants, or, in combined cycles with steam turbines to provide either mechanical propulsion or to generate electricity, which is subsequently used by electric drives to propel the ship. However, thermal efficiencies of gas turbines are lower than those of diesel engines of similar power. In the context of improving the performance of existing two-shaft marine gas turbines, it is proposed to enhance engines' performance by integrating a pressure wave supercharger, or wave rotor, while keeping the components of the baseline engine unchanged. Cycle analysis is performed at design point for the baseline engines, as well as for the topped with 4-port wave rotor engines. Important benefits are obtained for 4-port wave rotor-topped engines, including Recuperator in comparison to the self-standing baseline engines for the whole range of engines operation. It is found that the lower the compressor pressure ratio and the higher the turbine inlet temperature is, the more the benefit gain of the wave rotor-topped engine is attained in terms of thermal efficiency and specific power. Keywords: marine gas turbine, wave rotor, thermal efficiency, specific power, recuperator. Introduction. Greenhouse gas emissions, GHG, are considered primary source for an incontestable trend in global warming. Thus, pollution control is strongly recommended and lately established by law. NOx and SOx emissions produced by seagoing ships are of great concern in recent years. The International Maritime Organization, IMO, has imposed strict emission limitations by putting in force MARPOL Regulations 1. In a study of 3 alternative propulsion systems done in 2, it was concluded that gas turbine engines, GTEs, satisfy the IMO requirements and reduce significantly the machine room space and weight required with respect to the rest of the configurations examined, but additional efficiency improvement methods have to be incorporated in order to increase the relatively low efficiency of GTEs. Additional to the advantages of GTEs, the choice of LNG as fuel contributes substantially to the reduction of CO2 emissions. Moreover, the GTE combustion technology, with steady state and controlled flame temperature, allows significant reduction in NOx emissions, easily matching nitrogen regulations for current marine engines. 3. Development in gas turbine technology during the last years, made possible for a simple gas turbine cycle to attain levels of thermal efficiency of the order of 37%. Marine gas turbines have been almost exclusively developed by aero engines. High fuel prices dictate the need for efficiency improvement methods, resulting in major savings on fuel consumption and life cycle costs. One of the methods suggested to increase the thermal efficiency is to integrate to the baseline engine intercooling and regeneration, ICR. The predicted efficiency improvement is of the order of 20%. 4. Another method is to use combined cycles for ships. A first category is combines gas and steam turbine, COGAs, where the shafts of the turbines drive directly the propeller, and a second one is the combined gas turbine and steam turbine integrated electric generator, COGS. At full load, the COGAs configuration offers higher efficiency as the transmission efficiency is higher. With the COGS configuration, it is easier to achieve rational part load performance, because one or several power units can be shut off as the power is reduced while the remaining power units are operated at power conditions where they are efficient. 5. A genuine method proposed in this article for efficiency improvement with simultaneous power increase is the integration of a 4-port wave rotor into a marine gas turbine. A wave rotor, Fig. 1, is composed of a purely cylindrical rotor inside a casing. Circumferentially equidistant axial straight blades are formed between these cylinders. 2 stationary end-wall plates with perforated circumferential openings are mounted at the rotor extremities, allowing only partial inflow and outflow through the rotor blade channels, as described in 6 and 7. Depending on the number of openings, or ports, wave rotors can be classified as 3-port, 4-port, or 5-port configurations. Figure 1 illustrates a 4-port wave rotor configuration, which is the one best suited as a gas turbine topping device. 8. The rotor is connected via a ducting system to the compressor, turbine, and combustion chamber of the baseline engine. The principle of operation of wave rotors is based on propagation and interaction of unsteady pressure waves inside the channels formed by 2 consecutive purely radial blades of the rotor. These moving pressure waves are formed inside the wave rotor channels when a high enthalpy gas stream, e.g. hot combustion gas, is coming in contact for a short time so that mixing is avoided with low enthalpy gas, e.g. compressed air, being inside the rotor. According to the basic theory of gas dynamics in 6, the propagation of a compression wave inside each of the rotor channels results to the formation of an expansion wave and its propagation at the opposite direction. The contact discontinuity between the high and the low enthalpy gas streams guarantees that no mixing between the two streams will occur. When a wave rotor is integrated in a gas turbine, extra compression in the airflow is achieved by means of compression waves formed inside the wave rotor channels when hot exhaust gases coming out of the combustion chamber come in contact with air from the compressor. Simultaneously, expansion is achieved when expansion waves are directed at the outflow port towards the turbine. An efficient design of wave rotors is attained when the pressure waves inside the rotor result in uniform and steady flows at the outflow ports, so that the air flow towards the combustion chamber and the gas flow towards the turbine are uniform. For the case of the 4-port through-flow configuration, the rotor blades are self-cooled because hot gas and compressed air are traversing the rotor, cooling the blade material. Feasibility studies of integrating a wave rotor to aircraft gas turbines. 9. Predicted reduction of the specific fuel consumption and increase of the specific thrust delivered by the engine. Recently, the possibility of integrating a 4-port wave rotor also to industrial gas turbines was also explored. 10. This article is an original study on wave rotor technology applied to marine gas turbines used either as the unique propulsion system, or in combined cycles for propulsion. Performance assessment is performed for 2-shaft gas turbines with and without recuperator at design point conditions by means of the thermodynamic model developed. It is concluded that integration of wave rotor to a marine gas turbine improves the thermal efficiency of the engine and at the same time increases its specific power. The improvement is more remarkable for engines operating with low compressor pressure ratios, RC, and high turbine inlet temperatures, TIT, for the range of compressor pressure ratios examined. 2-shaft gas turbine calculations. Input data for 2-shaft gas turbines. The procedure of the thermodynamic calculations of 2-shaft gas turbine cycles with the integration of a 4-port wave rotor is described in detail in 11. It is based on standard thermodynamic analysis of gas turbines, as presented in 12, 13, adding the compression and expansion processes inside the wave rotor. Figure 2 illustrates the configurations for the wave rotor-topped 2-shaft gas turbines used in this article. Thermodynamic properties of combustion gases and air at various stages throughout the gas turbine cycle are calculated by considering variation of temperature according 14. In the equations below, TA and TG are the average temperatures during the compression and expansion processes in the compressor and turbine respectively. For air at low temperature range of 200 to 800 K. Constant values are assumed for the air and for the exhaust gases as, and Table 1 summarizes typical values of input data used, turbine inlet temperature, TIT, and the compressor pressure ratio 1.4 C. 1.333.h. Cr. Figure 3 illustrates the model developed to calculate the thermodynamic properties of air and hot gases when a 4-port wave rotor is integrated to a 2-shaft gas turbine. The 4-port configuration has been proposed by many researchers, 7, 9, 11 because it can be easily integrated to an existing gas turbine and it offers important performance enhancement of the baseline engine. In the 4-port configuration, schematically shown in Fig 3, when the hot exhaust gases from the combustion chamber exit enter the wave rotor from the hot port 4.2, they come in contact with the compressed air from the compressor which is already inside the rotor through the cold port 4.0 and has filled the space between the rotor blades. These two streams, i.e. the cold air and the hot exhaust gases, are brought into contact inside the rotor. 6. As a result, a compression wave is initiated which compresses further the air stream. The compression wave is propagating along the rotor, reflected on solid walls directed via the port 4.1 towards the combustion chamber. Simultaneously, an expansion wave is formed due to the contact of the streams of cold air and the hot gases. It is propagating to the opposite direction, with respect to the compression wave, reflected on solid walls directed towards the turbine through the port 4.3. The location of the inlet and outlet ports of the rotor depends on the unsteady wave interaction inside the rotor, called wave diagram, and its rotational speed, which is about 1/3 the rotational speed of the high-pressure turbine shaft. The wave-rotor pressure ratio is a very important parameter that characterizes the performance of the wave rotor and accordingly the performance of the whole gas turbine. It is defined as the pressure at the wave rotor outflow towards the turbine is given according to 8 by the following relation known as the wave rotor characteristic. C. Performance. The power consumed by the compressor, Cw. Power produced by the gas turbine is used to drive the compressor Tw. Heat added by the fuel Inq. Power produced by the power turbine, Ptw. Net power delivered by the engine, Nw. Specific power Ws. Thermal efficiency Th. Specific fuel consumption, SFC. The allowable temperature of metal used to manufacture the blades is approximately 800, 9,000 C, but the allowable surface temperature of blades has been increased up to 10,000 C due to the recent application of thermal barrier coatings on blade surfaces. 15. Thus, in the simulations, the surface temperature of the blades is set to be constant at 10,000 C. The present thermodynamic model accounts for cooling the turbine in case TIT 10,000 C by subtracting airflow from the high-pressure outflow port of the wave rotor. The coolant flow rate is determined by considering various operating parameters such as the operating temperature of the blades and the temperatures and specific heats of the main gas and coolant. The coolant flow rate at the design point is calculated using an energy balance equation based on the inlet air flow rate, power output, efficiency, gas turbine outlet temperature, and TIT according to the method proposed in 15, 16. Turbine blades are made of nickel or rhenium alloys capable of withstanding high heat without distortion. The high-pressure turbine airfoils as well as the power turbine airfoils are cooled. They are made of Inco 738 coated with a silicon aluminate coating. 18. 3-wave rotor-topped 2-shaft gas turbine. Figure 4 presents the performance curves of wave rotor-topped 2-shaft gas turbines at design point for various values of RC and TIT, illustrated with continuous lines in comparison to the baseline, without wave rotor, 2-shaft gas turbines illustrated with dotted lines. These results correspond to PR equals 1.8 and NE equals NC equals 0.83, values widely accepted in the literature, 8 to 11. Dotted lines with triangular symbols illustrate the performance of the baseline engines while continuous lines with spherical symbols of the same color illustrate the performance of the wave rotor-topped engines. Each symbol in the diagram corresponds to the design point conditions of a specific 2-shaft gas turbine. From this figure, it can be seen that for a given value of turbine inlet temperature, thermal efficiency of wave rotor-topped engines, as well as specific power are increasing with respect to their values of the baseline engines. As it is easily seen, the performance curves of the wave rotor-topped engines are shifted to the upper right part of the diagram. Figure 5 presents the SFC, WS distribution of wave rotor-topped 2-shaft gas turbines at design point conditions for various values of RC and TIT. One can observe that the performance curves of the wave rotor-topped engines are shifted to the lower right part of the diagram compared to the corresponding baseline gas turbines without wave rotor. Therefore the wave rotor integration decreases baseline engines SFC and simultaneously increases its WS. Figures 4 and 5 indicate that low values of the compressor pressure ratio, RC, are more favorable to the integration of a 4-port wave rotor to a gas turbine in terms of thermal efficiency, specific fuel consumption and specific power, especially at high values of TIT. Figure 6 shows qualitatively the effect of integrating a 4-port wave rotor on 2-shaft engines. In this figure, a typical case with PR equals 1.8, NC equals NE equals 0.83 for TIT equals 1500 K is presented. In the same figure, the percentage increase in WS, blue bars, and in nth, gray bars, are illustrated. A clear benefit in terms of WS and nth increase for all values of RC considered can be seen. More specifically, the prevalent increase in nth reaches 19.3% and in WS reaches 18% for compressor ratio RC equals 5. This increase decays as RC increases, ending up to a minimum value of 4.8% and 2.6% for nth and WS respectively, for RC equals 30. This means that for all range of gas turbines there is a clear performance enhancement. Figure 7 shows qualitatively the effect on specific fuel consumption of integrating a 4-port wave rotor on 2-shaft engines. A typical case with PR equals 1.8, NC equals NE equals 0.83 for TIT equals 1500 K is presented. The major decrease in SFC is 23.9% for RC equals 5, descending to 5% for RC equals 30. Conclusively from Figs 6 and 7, performance enhancement of 2-shaft wave rotor-topped engines operating at design point conditions having TIT equals 1500 K is maximized for low values of RC. Referring to Figs 4 and 5, it is concluded that the higher the TIT, especially for low values of RC, the more the benefits are for the engine's performance. 4-wave rotor recuperated gas turbines. In industrial gas turbine industry, fuel economy can be achieved by introducing a recuperator in the baseline engine. 11. This device recovers waste energy from the gas turbine exhaust, preheating the air entering the combustion chamber, improving cycle efficiency and reducing fuel consumption. 17. The development of the Rolls-Royce WR21 engine for marine applications is based on this concept. 18. Under this perspective, a 4-port wave rotor can be introduced to the basic gas turbine recuperator cycle, as illustrated in Fig 8. The thermodynamic calculation of the recuperator is based on an iterative procedure. Initially the temperature of the cold exit 5.2 of the heat exchanger is assumed, T05 HIP. Then fuel mass flow through the combustion chamber is. The hot exit temperature of the recuperator, T10, is calculated as. Where NHE is the efficiency of the recuperator, its value lies between 0.84 and 0.92. The updated value of the cold exit of the recuperator is calculated as. If the quantity is less than a prescribed error, e.g. 0.001, then the calculation is converged, otherwise a new value is assumed and a new iteration begins. 05,05,05 real hip real TTT. 05,05 hip real TT. The pressure loss in the recuperator is expressed by means of the recuperator pressure loss that takes values between 1% and 4%. The performance map of two-shaft wave rotor recuperated engines with respect to the corresponding two-shaft baseline recuperated engines at design point is shown in Fig. 9. HELOSP. As for the case of two-shaft wave rotor-topped engines without recuperator, shown in Fig. 4, it can be observed that for low values of RC, the integration of the wave rotor reduces significantly the engine's specific fuel consumption, especially at high values of TIT. At higher TIT values, the performance curves of the topped engines recover their expected fishhook shape. Figure 10 shows qualitatively the effect of integrating a 4-port wave rotor on two-shaft recuperated engines. A typical case with PR equals 1.8, NC equals NE equals 0.83 for TIT equals 1500 K is illustrated. In the same figure, the percentage increase in nth is shown. The specific power, Ws, is not affected by the presence of the recuperator. From this figure, it can be seen that there is a benefit in terms of nth increase for all values of RC considered. More specifically, the prevalent increase in nth reaches 22.6% for compressor ratio RC equals 5, whereas the minimum increase is never less than 19%. This increase is kept almost constant as RC increases, even for engines with RC equals 25 or 30. Figure 11 shows qualitatively the effect on specific fuel consumption when integrating a 4-port wave rotor on two-shaft recuperated engines. A typical case with PR equals 1.8, NC equals NE equals 0.83 for TIT equals 1500 K is presented. The decrease in SFC is as much as 29.2% for RC equals 5, and for RC equals 15 is 23.7%. From Figs 10 and 11, performance enhancement of two-shaft wave rotor-topped recuperated engines operating at design point conditions having TIT equals 1500 K is maximized for low values of RC, but there is a net benefit which is kept almost constant independent of the value of compressor pressure ratio. For the typical value of TIT examined, the net benefit in terms of thermal efficiency is more than 19% and the reduction in SFC is close to 24% for all compressor pressure ratio values examined. V. Integration challenges. The Rolls-Royce Allison 250 turboprop 2-shaft gas turbine integrating a 4-port wave rotor was built as a demonstrator 19. The original engine was modified to integrate the wave rotor and the associated ducting, keeping compressor, turbine and combustor the same. The rotor diameter and length were approximately equal to the tip diameter of the high-pressure turbine. The wave rotor was mounted on a separate shaft between the turbine and combustor. The rotor spins coaxially with the gas turbine shaft at approximately 1/3 the speed of the gas generator spool through its operating range. As far as it concerns power plant gas turbines, typical wave rotor diameter and length are similar to those of the baseline engine. It was found to produce 11.4% more shaft power, plus 20% specific power, with a 22% decrease in engine's SFC at design point conditions, values comparable with the present simulations. The greatest challenges are related to the design of the ducts connecting the combustion chamber to the turbine due to high temperatures, 20. As for the case of marine gas turbines, the integration of a 4-port wave rotor to an existing aeroderivative gas turbine is expected to increase the overall length of the engine as much as the turbine diameter, without any increase in the maximum diameter of the engine. A comparison between the wave rotor-topped 2-shaft recuperated gas turbines and the wave rotor-topped 2-shaft gas turbines is illustrated in Fig. 12. One can observe that the thermal efficiency of wave rotor-topped 2-shaft recuperated gas turbines is comparable to combined cycle efficiencies, surpassing 50% for values of TIT equals 1400 K, whereas the specific power is almost the same between the wave rotor-topped recuperated 2-shaft and the wave rotor-topped engines. From this figure, it can be also seen that the integration of a wave rotor to a 2-shaft recuperated engine favors engines with low compressor pressure ratios, RC. For 2-shaft topped engines the highest thermal efficiencies are attained to intermediate values of RC. The expected merits of wave rotors for marine propulsion systems include implementation to naval and commercial ships, implementation to existing aeroderivative gas turbines without major changes to the basic components, increase in thermal efficiency of the baseline engine, increase in specific power of the baseline engine, reduction in specific fuel consumption of the baseline engine, increment only in engine's length without significant changes in other dimensions and weight. Possibility of in-rotor constant volume combustion. 21. Replacing the conventional combustion chamber of gas turbines. Possible demerits are related to the fact that the wave rotor technology, being novel and under development, needs investments to be conducted in design and manufacturing of necessary ducting to connect the wave rotor to existing components of the gas turbine. Cooling requirements of the ducts connecting combustion chamber exit to wave rotor hot inlet port. Manufacturing of prototypes for experimental performance validation and design optimization of wave rotor-topped engines. Conclusions. In this article, performance assessment of two-shaft gas turbine engines topped with a 4-port wave rotor as a prime mover or combined with steam turbines for seagoing ships was performed. Integration of wave rotor technology in marine gas turbines can moderate the fuel consumption and increase the specific power of the engine. In marine gas turbines, the extra weight of the wave rotor-topped engine is negligible with respect to the weight of the ship, and the extra dimensioning due to the wave rotor and the associated ducting do not impose major changes in the machine room. In the thermodynamic model developed, the compressor, gas turbine and compressor turbine of the baseline engine are kept unchanged to keep the wave rotor's integration cost low. Ambient pressure and temperature, thermodynamic constants for the air and hot gases, thermal efficiencies for compressor, compressor turbine, and power turbine, as well as compression and expansion efficiencies for the processes inside the wave rotor, are the input data required. Performance maps at design point illustrate the benefits of wave rotor-topped engines with respect to the corresponding baseline engines. Depending on the design requirements concerning specific power and specific fuel consumption, the topped engines maps help to select the most favorable engine and its precise operating conditions, compressor pressure ratio, turbine inlet temperature. For two-shaft engines working at a given compressor pressure ratio, the higher the turbine inlet temperature is, the more the benefit gain of the wave rotor-topped engine is attained in terms of thermal efficiency, specific fuel consumption and specific power. Assuming compression and expansion efficiencies inside the wave rotor, as well as ducting and leakage pressure losses specified in the literature 10.11, it was calculated for typical aeroderivative engines, such as the GELM2500 series of the RR Olympus, that the increase in thermal efficiency remains higher than 8% and the increase in specific power remains higher than 6% at TIT equals 1500 K. For the case of wave rotor-topped recuperated gas turbine engines, the thermal efficiency increases by at least 19% and the specific fuel consumption decreases by at least 24% for all pressure ratios examined for TIT equals 1500 K with respect to the baseline recuperated engines. Peak thermal efficiency can exceed 50% for TIT equals 1400 K and low values of the compressor pressure ratio. 4-port wave rotors have the potential to enhance the performance of marine gas turbines, although there are challenges to be successfully exceeded.